Some objects pass through space unnoticed. They arrive silently, follow predictable paths, and disappear without consequence. Others pass through briefly and leave behind questions that refuse to settle. 3I Atlas belongs to the second category. When astronomers first identified the object, later designated as 3I Atlas, nothing about it triggered immediate concern. Interstellar visitors, while rare, are not unprecedented. Objects are routinely ejected from distant star systems through gravitational disruption, stellar encounters, or the chaotic processes of planetary formation. Once expelled, they wander the galaxy for millions, sometimes billions of years before briefly crossing another star's domain. Most of these visitors behave predictably. They drift, they tumble, they respond passively to radiation, gravity, and heat. 3I Atlas did not. The first indication that something was different appeared not in brightness or composition, but in motion. Orbital calculations revealed a hyperbolic trajectory, meaning the object was not gravitationally bound to the Sun. This was not a body looping inward or settling into orbit, it was passing through, and it was moving fast. Its velocity exceeded solar escape velocity by a wide margin. In practical terms, the Sun could not slow it down, could not capture it, could not significantly alter its course. That fact alone confirmed its interstellar origin. But speed was only the opening detail. As Atlas moved deeper into the solar system, astronomers initiated coordinated observation, not to announce a discovery, but to eliminate error. Independent instruments operating under entirely different conditions were tasked with observing the same object. The James Webb Space Telescope recorded infrared signatures. Hubble provided visible light imaging. Ground-based observatories contributed high-resolution spectroscopic measurements. The data converged. What it revealed was unexpected. Sensors detected motion originating from within the object itself. This was not surface shedding, it was not debris being pushed outward by solar heating. The displacement appeared internal, directional, and persistent, as though mass inside Atlas was shifting rather than escaping. In physics, this distinction matters. Surface activity dissipates energy outward, it reacts, it erodes. Internal movement suggests resistance, something responding to stress rather than simply absorbing it. Initially, researchers treated the signal as noise. Deep space observations frequently contain false positives. Instruments were recalibrated. Background interference was stripped away. Timestamps were cross-checked across observatories. The anomaly remained. Then came the second irregularity. Thermal sensors registered a sudden temperature drop inside Atlas's core, nearly 100 degrees Celsius. The change was rapid. It was not gradual cooling caused by rotation, shadowing, or distance from the Sun. Atlas had not entered a region of reduced solar exposure. For an object bathed in sunlight, such a drop implied something unusual. Active heat absorption, not passive cooling. And then came the pulses. Electromagnetic detectors recorded a sharp emission, then another, then another. Each occurred at precise, evenly spaced intervals. The timing did not drift, it did not decay, it repeated. In nature, regularity of this kind is rare. Gas outgassing produces chaotic bursts. Fracturing ice releases energy unpredictably. Even crystalline stress responses vary in timing and intensity. The emissions from Atlas did not. NASA's public description was deliberately cautious. The phenomenon was labeled an unclassified thermodynamic fluctuation, accurate but intentionally non-committal. Within scientific discussions, however, another word appeared more often. In science, an anomaly is not a conclusion, it is a warning. As Atlas approached Jupiter, the data became harder to ignore. Jupiter possesses the strongest magnetic field in the solar system. Its magnetosphere stretches millions of kilometers into space, interacting with charged particles far beyond the planet itself. It is not merely a planet, It is a dynamic electromagnetic environment. As Atlas entered this region, subtle changes occurred. Emission intensity shifted. Spectral lines fluctuated. Internal motion coincided with localized magnetic field variations. The activity did not begin randomly. It intensified under specific conditions. Correlation is not causation. But in physics, correlation demands explanation. Researchers avoided charged language. No one described the behavior as communication. No one referred to it as a signal. Yet internal notes acknowledged something more difficult to dismiss. The behavior was non-random. Whatever was occurring inside Atlas appeared responsive, condition-based, rather than accidental. The question was no longer what is happening, it became why here? And that question would define the next phase of the investigation. By the time 3I Atlas exited Jupiter's immediate influence, the tone of scientific discussion had changed. Early curiosity gave way to restraint. Atlas was no longer being asked what it is, it was being examined for what it is not. In science, elimination is often more powerful than discovery. The first explanation to be tested was the most familiar: cometary outgassing. When volatile compounds warm, they sublimate and escape through surface vents, generating thrust. This process explains jets, changes in rotation, and tail formation in countless known objects. But Atlas resisted this explanation. Outgassing originates near the surface. The motion detected in Atlas did not. It appeared deep within the structure, subtle, directional, and persistent. More importantly, gas-driven activity is inherently chaotic. It varies with temperature, pressure, and structural weakness. The emissions observed from Atlas did not. They followed a precise rhythm. Nature rarely keeps perfect time without feedback. Next came thermal cracking. Unheating can create stress fractures, releasing energy and material. This mechanism explains sudden brightness changes in some comets and asteroids. But thermal cracking releases energy outward. It does not produce rapid internal heat absorption. It does not generate electromagnetic pulses at fixed intervals. And it does not synchronize with magnetic field fluctuations. Ice sublimation was also considered. Different ices respond at different temperatures, and layered composition could explain uneven activity across the object. But sublimation lacks memory. It erupts, it fades. It does not pause, reset, and repeat with identical timing. Crystalline flexing, another exotic but natural explanation, also fell short. Some crystal structures can store stress and release it under radiation. But crystalline behavior does not coordinate motion, thermal change, and magnetic response into a clean, ordered sequence. Each explanation failed, not because it was impossible, but because it was incomplete. This is where uncertainty sharpened. If Atlas was not merely reacting to its environment, researchers had to consider whether its internal structure was fundamentally different from existing models. Not artificial, not intentional, just unfamiliar. This line of reasoning led to what became known as the shell hypothesis. The shell hypothesis proposes that Atlas may consist of a dense outer layer encasing a complex, heterogeneous interior. Such a structure could form naturally under extreme interstellar conditions. Over millions of years, radiation exposure, micrometeorite impacts, and thermal cycling could harden the exterior while preserving volatile-rich material beneath. A shell would explain several observations at once. It would isolate internal processes from surface behavior. It would allow heat to be absorbed internally without immediate surface response. It would permit long dormancy, followed by brief activation when specific thresholds were crossed. Jupiter may have provided that threshold. Jupiter possesses the strongest magnetic field in the solar system. Its magnetosphere stretches millions of kilometers into space, interacting with charged particles far beyond the planet itself. As Atlas passed through this region, subtle but measurable changes occurred. If Atlas contains conductive or magnetically sensitive material, Jupiter's magnetosphere could induce internal currents, not to power the object, but to trigger dormant processes already present. This interpretation remains speculative. Natural bodies can respond to magnetic stress without design. Interstellar objects may contain materials rarely encountered in our solar system, but the timing raised an unavoidable question. Why remain dormant for millions of years only to activate here? As Atlas continued its passage, another anomaly emerged. The object began to change shape rapidly. Images taken days apart showed elongation and internal asymmetry. The tail split. The coma stretched. Yet the overall thrust direction remained stable, suggesting that the same internal regions were intensifying rather than new ones forming. This pointed toward deepening fractures rather than surface chaos. Spectral analysis supported this view. Larger particles dominated some regions, finer dust dominated others. Infrared data revealed thermal inversion, with outer layers retaining more heat than the core. These observations suggested exposure of ancient internal layers, material that had not interacted with starlight since Atlas formed around another star. In this framework, Atlas was not becoming something new, it was revealing something old. Despite the dramatic behavior, no physical laws were broken. Atlas expanded the range of known behavior without violating rules. That distinction guided scientific restraint. Speculation followed public interest. Claims of secrecy spread online. None were supported by evidence. When official data resumed, the images showed nothing extraordinary, only a highly unusual object moving away from the sun. By then, the most active phase had passed. Atlas exited the solar system carrying its unanswered questions with it. No final confirmation was possible. No decisive test could be performed. And that incompleteness became the conclusion. 3. Atlas did not prove intent. It did not prove design. It proved something more challenging. That our models are incomplete. And that the universe still knows how to surprise us. In science, that is not failure. It is the frontier.